Okay, today's problem is analyze the indeterminate continuous beam shown in the figure. So here CD is a overhang portion and the span BC carries 80 kilonewton per meter load and the span BAP carries a point load of 90 kilonewton at an eccentric distance of 2 meters from end A and 4 meters from end B. So now, this particular portion of the beam, that is CD, is a determinate one because it gives the moment at C is nothing but equal to, consider right of the section 60 into span CD. Span CD is 2 meter. So we can replace this particular beam by means of an equivalent beam by equivalent continuous beam, that is ABC. So the next figure, equivalent beam, you can write only two rollers, right? So at C, you need to represent the effect of 60 kilonewton as 120 kilonewton meters. So this particular beam we call it as equivalent beam. So similarly, other loads which are acting on the beam. So a point load of 90 kilonewton and UDL of 80 kilonewton meters. So this particular beam, as I told you, it is called as an equivalent beam because a cantilever portion is a determinate one, and this cantilever portion can be removed by means of showing the effect of 60 kilonewton force at C. The effect is nothing but 60 into 2, 120 kilonewton meter. Moment is acting at point C. So now the next step is determine degree of freedom. Degree of freedom. So to determine the degree of freedom, see, at support A, it is a fixed one. Therefore, it can take up all three types of forces, that is vertical reaction, horizontal reaction, and moment. So this joint do not have any degree of freedom. Coming to roller, it can take up only vertical reaction. Since no horizontal forces are acting on the beam, the horizontal forces are not going to come into effect. Therefore, but this joint can rotate. So there is a degree of freedom, one number at the support, that is B. Similarly, at support B, there can be rotation of the joint. Therefore, the total degree of freedom of the structure can be called to be 2. Once you determine the degree of freedom, next is assign the coordinates at these particular points. So, I will assign the coordinates in the next figure. So I assign coordinate number 1 and coordinate number 2 at point C. So now we will restrain the different portions of the beam and we will find the fixed dead moments. Restrain the beam by means of assuming supports B and C to be a fixed one. So this particular beam is called restrained structure. So it carries a load of 90 kilonewton and span BC carries uniformly distributed load and a moment 120 kilonewton meters. So now determine the fixed moments for the different spans. So AB carries an eccentric load of 90 kilonewton. Therefore, the next step, I'll go for the fixed moments. Because to generate the column of external forces, effect of external forces on the beam, these fixed end moments are required. So I call the fixed end moment as MFAB, which is equal to MFAB acts here, and it is equal to minus WAB square by L square. These formulas you need to remember. Minus WAB square by L square. Now substituting the values 90 into 2 into 4 square divided by 6 square. So you are going to get minus 80 kilonewton meters as the fixed end moment. So minus 80 kilonewton meters is the fixed end moment at the support A for span AB. Similarly, MFBA, that is fixed end moment at support B for the span, that is AB, is nothing but equal to plus WBA square by L square. So substituting the values 90 into B is 6 into A square, 2 square divided by L square, that is 6 square. So now I get the fixed end moment at B as equal to 40 kilonewton meters. 40 kilonewton meters. Now for the span BC, UDL is acting over the entire span. Therefore, MFBC is equal to minus WL square by 12. So it is equal to 80 into 4 square. Okay, distance I have not given here. It is nothing but 4 meters. BC is 4 meters. So 4 square divided by 12. So you get minus 106.67 kilonewton meters. Next is fixed end moment for at C for the span BC. We can call it as MFCB equals to plus WL square by 12. Already it is calculated with negative sign, so directly take 106.67 kilonewton meters. Now you can generate the force matrix, that is effect of external forces acting on the beam. So the force matrix we can generate it as PL is equal to, that is force acting at coordinate number 1. It has got two number of moments, one for the span BC and another for the span AB. So PL is nothing but equal to, we can say P1 and P2. So it is equal to, see at B, two forces are acting, that is MFBA and MFBC at coordinate number 1. So P1 is the net force acting at coordinate number 1, that is equal to plus 40 minus 106.67. Then coming to coordinate number 2, only one moment, one fixed end moment is acting, that is equal to MFCB, that is 106.67. So we have generated the force matrix in the form of PL. Next is, we will go for the development of the stiffness matrix elements. So to develop the stiffness matrix, you need to apply unit rotation at the coordinates 1 and 2 separately, and then determine these things by applying slope diffraction equations, or you can avoid slope diffraction equations because when one radial rotation is given at say joint B, we need to apply a moment equal to 4EI by L. And this 4EI by L is carried over to the opposite joint by 50%. Similarly, to rotate this member BC and B by one radian, you need to once again apply 4EI by L for this particular span. So now I call this as development of stiffness matrix. So now the next figure, apply unit rotation at B. Right, assuming all the supports to be fixed, apply unit rotation at B. So here, the force required at this junction, we call it as K11. That is, force required at coordinate number 1 when unit load is applied at coordinate 1. Similarly, coordinate number 2, we can call it as K21. That is, force induced at this joint when unit load is applied at coordinate number 1. So here we are giving unit rotation that is theta b equal to 1. So now we can go for development of the stiffness matrix elements. So stiffness matrix elements. So delta 11 is equal to 4EI by L for span AB or span BA plus 4EI by L for span BC. So substitute the values. DI is assumed to be constant. Okay, DI changes are not given in the figure. 2I and this is I. So now for this particular span AB, 4E into 2I divided by L. L is 6 meter plus 4EI by L for span BC. So for this span BC, I is I itself, therefore 4EI by 4. So ultimately, you are going to get this as 4 into 2 is 6. Totally, you are going to get this as equal to 7 by 3 EI. On simplification, you are going to get K11 as equal to 7 by 3 EI. Next is K21. K21 means, see, when I apply unit rotation at this particular joint is going to receive half of 48 by L at this 48 by L at junction A, and again whatever moment 48 by L for span BC I apply, 50% of that will go to the joint C. Therefore, we can say it is 2EI by L, and it is only for one span. Therefore, it is 2EI by 6. Or we can say EI by L is 4 meter Therefore, we get 0.5 EI. Now, you apply unit rotation at coordinate number 2, that is at point C. So when I apply unit rotation at coordinate number 2, so I am applying theta equals to 1 at C. Theta C equal to 1. So now when we apply this to produce unit rotation at of the span CB by applying the force or moment, 4 by L is required to be applied for this span at C. This will contribute 50% of that moment to the opposite joint or the joint at the far end. Therefore, the next elements are K12, that is rotation at coordinate number 1 due to application of load at coordinate number 2, that is equal to 50% of this 2EI by L, that is 2EI by 4. So you are going to get this also as 0.5 EI. Similarly, K22, that is force exerted at coordinate number 2 due to application of unit rotation at coordinate number 2 is equal to 4EI by L for the span BC. So 4EI, L is 4 meter. So you are going to get this as EI. See, we can now develop the stiffness matrix. We have developed the stiffness matrix equation. Now we can formulate this into matrix format. So to develop this into matrix format, we have the formula, that is K matrix multiplied by delta matrix is equal to P minus PL. P minus PL. So now we can write the equations for, we can substitute the values from the known data. So now we can say K is nothing but K11 is 7 by 3 EI. K12 is 0.5 EI. K21 is also 0.5 EI. And this is simply 1 EI. Into delta matrix. Delta matrix means theta A and theta B. That is our delta matrix. So we can write this as either delta 1 or theta 1 or theta B, and delta 2, which is nothing but theta C. This is equal to P minus P. P is already we have determined this. See, at coordinate number 1, P value is equal to 66.7. And at coordinate number 2, already a moment is there in clockwise direction, 120 minus 106.67. So you can refer these values, these two values we have in the very early matrix formulation of force due to external loads. So now you can bring out EI by 3 as common, EI by 3 into 7 and 1.5 get 0.5. If you multiply it by 3, you are going to get 1.5, again 1.5, and multiply this by 3, you get 3. into, okay, right, theta B and theta C is equal to 66.7. 120 minus this one, you get 30.3. Now, our objective is to determine theta B and theta C. Therefore, you can bring this to the right hand side, rearrange it to get the final matrix format. So, I can write in the next one, theta B and theta C is equal to 3 by EI. If it comes to the right hand side, it becomes 3 by EI into 7, 1.5, 1.53. This is inverse. When it comes to the right hand side, it becomes inverse. Multiplied by 66.7 and 13.3. So now, if you solve the problem by using your calculator, going for matrix this one, you are going to get the values of theta B equal to 28.802 divided by EI, and theta C equals to, you get minus 1.107, sorry, 0.17 divided by EI. See, once we determine the values of theta B and theta C, which were applied at coordinate number 1 and 2, next is to determine the final moment developed in that particular in the particular given B. So now we will go for the final moments. What you require is you require to apply slope deflection equations for different straps. So making use of the slope deflection equations, we can find the final forces in all the members. So final moments MAP is equal to MFAB plus 2EI by L. I am writing the slope deflection equation generally, and later on we will substitute 2EI by L into 2 theta A nearer end, 2 theta A plus theta B minus 3 delta by L. Of course, this is the general equation I am writing. In the next equations, I will not use this 3 delta by L because there is no sink in the continuous beam. So now, MFAB you have already determined this as equal to minus 80. Minus 80, the fixed end moment, plus 2EI by L, 2 into E. I for this is 2I by L into theta A. Theta A is 0. Theta A is 0. Why is 0? Because it is a fixed end. It is a fixed support. Therefore, slope and deflection at the fixed support are going to be 0. So, directly 2AM theta A I am writing 0 plus theta B 28.802 divided by EI. So if you multiply E and I, they get cancelled themselves. Next, you can simplify the remaining part. You are going to get the final moment MAB as equal to minus 60.80 kilonewton meters. Next is MBA is equal to fixed net moment at B, MFBA plus 2EI by L. Okay, L also you can substitute. L is 6 meter. 2EI by L into 2 theta B plus 1 time the slope at A minus 3 delta by L. This is general equation. Again, this is 0. Now substitute theta B and theta A from the known values as fixed. A is a fixed support. Theta A is equal to 0. So now MFAB works out to be plus 40 plus 2E into 2I. I value is 2I and 6 meter is the span. 2 into theta B 28.802 divided by EI plus 0. So this moment you are going to get this moment you are going to get this as 78.403. 78.403 kilonewton meters. Next is, we will go for the next determination of force, that is MBC. So MBC, once again I will write the general slope equation, MFBC plus 2EI by L into 2 theta B here, rotation at the near end plus rotation at the far end, that is theta C plus 3EI by L, I write it 0 there. So now substitute the values. MFBC was determined to be minus 106.67 plus I is I itself, therefore 2EI by 4 into 2 into theta B, 2 into 28.802 by EI plus theta C. Theta C is minus 1.017 by EI. So on simplifying this, you are going to get MBC as equal to minus 78.403 kilonewton meters. Next we will go for the next one. MCB is equal to MFCB, fixed head moment at C, plus 2EI by L. 2EI by L, L into 2 theta C plus theta B minus 3 delta by L, minus 3 delta by L. I am not going to consider because it is 0. So now substitute the things. MFBC was determined to be 106.67 plus 2EI by 4 into 2 theta C, that is 2 into minus 1.017 by EI plus theta B. Theta B is 28.802 divided by EI. So EI automatically gets cancelled and the final MFCB you get it as 120 kilonewton meters. See here MCB you need to get 120 because for the equilibrium of joint C already there is cantilever effect. That is in opposite direction. We have got 120 in clockwise direction due to the moment. So to balance that, there will be an opposite anti-clockwise movement of magnitude 120 kilonewton meters. So all the final forces are determined. Next is we can go for drawing the bending moment diagram. So coming to the bending moment diagram, first plot the negative values. At A, MA is negative. You get MAB minus 60.80. So I can have a coordinate, and MBA is nothing but 78.403. So it will go to 78.403. See, it is said for this square BC you got minus 78.403, and the moment at this point is 120. So at the free end of the cantilever, the moment is going to be 0. It closes to 0. This is negative bending moment diagram. Now superimpose the free bending moment diagram. See, it is a triangle with W, AB, triangle, and under this node it is parabolic with maximum ordinate WL square by 8. This ordinate will be equal to WL square by 8. This is equal to WAB by 12. So this moment is positive and this moment is negative. Again, this is negative moment. This is again positive moment. This is again negative moment. So you can share the figure. So with this, the problem is complete. Okay, if you have any doubts, you can ask me. I hope this is the second problem what I am solving on continuous beams, because there is something speciality compared to the previous problem. This problem, a cantilever or an overhang is given. So when an overhang is given, it is a determinate part of the structure. So its effect can be considered in the form of movement. That is the only difference between the previous problem and this problem what I solved in the class.